All right, let's take a trip back to 1982 to a really foundational paper by a physicist named John Hopfield. He completely reframed how we think about computation by asking a pretty profound question. Could a complex ability, like memory, be a spontaneous property of a network instead of something that's meticulously programmed? So let's unpack his revolutionary answer. Before we dive in, let's just stop and appreciate the everyday miracle of our own memory. It's something we totally take for granted, right? But this ability to pull a complete, detailed memory from just a tiny, fuzzy clue is honestly one of the most powerful and mysterious computational feats we know of. Hopfield kicks off his paper with this exact problem. Imagine you're a scientist and you're trying to recall a specific paper. You only remember this tiny fragment, a name and a year. And yet, almost instantly, the full, correct reference just pops into your head. How on earth does the brain do that? Turns out, this incredible superpower actually has a name: content addressable memory. The big idea here is that you don't need a specific file name or an index number to find a memory. Any part of the content itself is enough to pull up the whole thing, even if your clue is a little bit wrong. Our brains are absolute masters at this. Traditional computers? Yeah, not so much. And this is where John Hopfield enters the picture. Now, the key thing to know about him is that he wasn't your typical computer scientist or neurobiologist. He was a physicist, and he looked at the brain not as a computer you have to program, but as a physical system, kind of like a collection of magnets with its own built-in behaviors. And his whole approach is summed up perfectly in this quote from his paper. So what's he really asking here? Well, think about it. You take a bunch of simple iron atoms, and when they interact in the right way, they can collectively create a powerful, stable magnetic field. Hopfield wondered, could a bunch of simple neurons, just by interacting, collectively create something useful, like a stable memory? In other words, can computation just emerge? Okay, this slide right here is the absolute core of the whole idea. It lays out this amazing analogy. In physics, systems always tend to settle into their lowest energy state. Just think of a ball rolling to the bottom of a valley. Hopfield proposed that a memory is exactly that, a stable, low-energy state for a network of neurons. The act of remembering is just the network settling into one of these stable spots. So if you're going to model this, you've got to build a brain, right? Or at least a simplified version of one. And Hopfield's model was so revolutionary because of its beautiful, beautiful simplicity. He boiled it all down to a few key ingredients. First, you've got super simple neurons that are either on or off, nothing fancy. Then you have connections between them, each with a certain strength. But here are the two things that were total game changers. One, strong feedback loops. So neurons are influencing each other all over the place. And two, asynchronous processing. There's no central clock telling all the neurons when to fire. Each one just checks its inputs and decides to flip its state whenever, randomly and on its own. This was way more realistic. And the rule that makes this whole thing tick? It is brilliantly simple. A neuron, just on its own time, looks at all its neighbors, it adds up all the incoming signals. If that total is above some threshold, it turns on. If not, it turns off. That's it. That is the entire algorithm. No master plan, no central CPU, just a simple local rule repeated over and over. Okay, so this super simple rule gives rise to this incredibly powerful and honestly beautiful idea that makes the whole system just click. Hopfield visualized the network's state as existing inside what he called an energy landscape. He came up with a single number for the entire network, which he called energy. You can kind of think of it as the total amount of disagreement or tension in the system. The memories you store in the network, they get carved into this landscape as deep valleys. These are the points of minimum energy, where everything is stable. And with that one concept, we get this perfect, simple analogy. The entire complex process of memory recall is really nothing more than a ball rolling to the bottom of the nearest hill. So, when you feed the network a partial or noisy clue, like Anne Wanier, 1941, what you're really doing is placing that ball somewhere on the side of a hill in this energy landscape. It's an unstable, high-energy state because all the neurons aren't quite in agreement yet. And then, the network just does its thing. As each neuron follows its simple little rule, flipping on or off to better agree with its neighbors, it slightly reduces the total energy of the whole system. This is literally the ball rolling downhill, step by step, always moving towards a more stable setup. And where does the ball finally stop? Well, it stops at the bottom of the closest valley.
that final, stable, low-energy state, is the complete, correct memory. The network has spontaneously corrected the errors and filled in all the missing pieces, all without a central boss telling it what to do.
So this simple ball rolling downhill model, it gives the network some legit superpowers. And these aren't things that were explicitly programmed in. They just emerge from the whole collective dance. It's a natural error corrector, like we saw. It also groups things together. Any input that's even vaguely similar will roll into the same memory valley. It can even recognize familiarity. If you give it an input that starts way up on a high plateau, far from any valley, the network knows this is something it's never seen before. And this last one is huge. It's fail-soft. The memory is stored everywhere, so you can lose a few neurons here and there, and the system still works, just maybe a little less perfectly. And here we see that error correction in action, plain and simple. You feed it a garbled input, Vanier with a V, that puts the ball on a hillside. It then just rolls down into the correct valley, and the output is the clean, complete reference. It's like autocomplete and spell check all rolled into one, and it just happens. But like any superpower, it has its kryptonite. There is a catch, and it's a really fascinating one. The network is not infinitely powerful. Hopfield did the math and ran the simulations. For a network with n neurons, you can reliably store about 0.15 times n memories. If you try to cram in any more than that, the energy valleys start to blur together, the network gets confused, and it can't recall things properly. There's a fundamental limit. So why are we talking about a paper from over 40 years ago? What does it all mean today? Well, because the ideas in this paper have had this massive, lasting legacy that still echoes through the foundations of modern AI. The huge takeaway, the thing that's just as mind-blowing today as it was in 1982, is this. You don't always need a complex, top-down plan to get complex behavior. Hopfield showed that the magic can happen spontaneously, from the bottom up, just from the simple interactions of many simple parts. And that leaves us with one last, kind of mind-bending thought. If a powerful ability like content-addressable memory can just emerge from a simple physical system following a few simple rules, what else can? It really forces us to ask a much deeper question about what intelligence really is, and whether it's less about some grand design and more about the beautiful, chaotic, and collective dance of simple things.